In this video, we're going to be taking a look at an oscillating mass connected to a spring, and we're going to be developing 5 different graphs so that you know how to develop any kind of simple harmonic motion type graph. We're going to go over one with kinetic energy, gravitational potential energy, and then on the bottom row, we have position, velocity, and acceleration. Now, although this is a specific scenario, we have a block hanging from a spring vertically, it does apply to a lot of other situations that are similar, such as a pendulum or a block on a spring horizontally. There's going to be some slight differences for those, but you're going to use the same types of skills and ideas. So let's go over a few ideas before we start drawing up our first graph. So we have an object that's at equilibrium, and then when you stretch it as much as you possibly can, it has its greatest negative x position and its greatest positive restorative force that is pulling it upwards. And then from there, it accelerates upwards. It has its maximum velocity at the equilibrium position right over here. And then it starts to compress the spring, slow down, and then reach a velocity of 0 at its maximum positive x position, where it has its greatest negative restorative force that's compressing and pushing it down. So I'm going to label this purple and green. So when we talk about these different sections, you'll know if I'm talking about the first part of its motion or the second half of the motion. So let's take a look at the kinetic energy. Kinetic energy is 1/2 mv squared. So we're mostly focused on the velocity because the mass is staying constant. And as you notice, the velocity is squared. So the velocity will not be negative at any point. We're going to stay above 0 for our graph. Now for the kinetic energy graph, we're going to start by pushing the spring all the way up to its greatest positive x position where the velocity is 0. When it's released from there, it's going to accelerate, and it's going to accelerate to its greatest velocity until it hits its equilibrium position. So it's going to be at the positive x position, accelerate to the equilibrium position where it's going to reach its maximum speed. And then it's going to still have a velocity, but it's going to slow down until it reaches its negative x position and then hits a velocity of 0 once again. And then as the spring gets stretched, it's going to pull it up and increase the velocity more and more and more until it reaches its maximum velocity again at the equilibrium position. And then as the spring starts to compress again, it's going to slow down and then reach a velocity of 0 once again. Now that's going to be one full period for the kinetic energy graph because we went from the positive x position back to the positive x position once again. Now we're going to do the same thing, taking a look at the gravitational potential energy. And for the gravitational potential energy, the formula is mgh. The mass is going to be constant, g is going to be constant, and h is going to be the factor that changes the value of the gravitational potential energy. Now, since we call the equilibrium position 0, we will have positive and negative heights. So again, we're going to be starting by compressing the spring all the way with the greatest positive position. So we're going to start right up here at the positive x position. And then from there, the spring is going to get pushed down and it's going to accelerate towards 0. And 0 height is going to be the equilibrium position over here. And then it's going to continue to go lower and lower to its greatest negative position. Now, when the spring is stretched all the way down, it's going to accelerate up again through its equilibrium position. And then from there, it's going to slow down as the spring gets compressed. And then the cycle is complete as it reaches its greatest positive x position once again. And that is one full cycle, one full period for the gravitational potential energy. Now let's take a look at the position versus time graph. So remember, position, you are literally thinking about where the block is located at a specific time. So we're starting at the greatest positive x position where the spring is completely compressed. And then it's going to accelerate quickly towards 0, where it reaches its equilibrium position and it has its greatest slope. And then from there, it's going to start to slow down and reach its greatest negative x position and stretch the spring out. and then the spring is going to give it the most amount of force, restorative force, and pull it up through its equilibrium position, again, where its greatest slope and greatest velocity would be. And then that slope is going to start to flatten out and then bring it to a rest at its greatest positive x position. And as you may have already noticed, the purple graph and the orange graph look very similar to each other, the position versus time graph and the gravitational potential energy, because both of them are based on the position. This position is just called the height, and then this one is literally called the position versus time graph. Now let's take a look at the velocity versus time graph. So we're pushing the spring all the way up where it is at rest. So we're going to be starting at 0. We're going to be thinking about how fast the object is moving. Now, when it's compressed all the way, it's going to get pushed downwards, which means it's going to have a greater and greater negative velocity. And then it's going to have its greatest negative velocity when it hits its equilibrium position, because there's no restorative force trying to slow it down. And then that negative velocity is going to get smaller and smaller and reach 0. So remember, when you're underneath the x-axis, although the line is going up, that is a decreasing negative velocity because you're heading towards 0. Negative is just to indicate that it's moving downwards. So then it hits 0 again when it reaches its negative x position. And this was the positive x position to start. And then from there, the spring pulls it upwards, accelerates it in the upwards positive direction to reach its maximum positive velocity through the equilibrium position. And then it starts to slow down as the spring gets compressed. And then we hit the positive x position again for that full cycle. Now, the very last one, we're going to take a look at the acceleration versus time graph. For me personally, I think it's easiest to think about the accelerations in terms of forces. So since force is directly proportional to the acceleration, if you think about how the forces get greater or smaller, that directly relates to the acceleration, and you can draw the acceleration graph that way. So if you compress a spring to its greatest positive x position, that's where it has its greatest amount of force that's pushing it downwards. So that's the negative direction. So we're going to have the greatest negative force and the greatest negative acceleration. Now from there, it gets pushed downward, and then as that spring gets less and less compressed, it's going to have no force at its equilibrium position. And then as a spring passes the 0 point and enters the green section, then the spring is going to start to get stretched, and then it's going to pull upwards in the positive direction, and that's going to pull more and more and more until it hits the negative x position. And then now that it's at its greatest negative x position, it's going to be pulling up as much as it possibly can, but then less, and less as it accelerates towards its equilibrium position. And then after it passes the equilibrium position, it's going to start to compress the spring as it goes through this second purple half. And as it compresses the spring here, the spring is going to compress it more and more, which is going to bring us back to our greatest positive x position and our greatest negative acceleration, because it's our greatest negative force pushing downward. Now for these simple harmonic motion graphs, as you can see, they all have similar curves, but in order to identify its beginning position and then how it moves up and down, you're going to have to think about all those different concepts of force, position, velocity, and so on. So I hope that was helpful in helping you analyze this oscillating spring and producing those 5 graphs. Thank you for watching and listening.